And two of our most favorite workloads of all time are 100% sequential and 100% random. So 100% sequential, what is this workload? How, like, what is practical example of this workload? For example, if you are searching a word in the file, it might lead to a 100% sequential workload. Again, it depends on different intermediate levels that we have and how they are processing this search query, but probably searching for word in the file, depending on your searching algorithm, if we are using a linear search, then it would lead to sequential IO. Okay. If you're using more advanced search like binary search or something, it may not lead to a sequential IO, or it may lead to like a partially sequential IO, not 100% sequential IO. Second, random. A practical example of a random workload, well, you can come up with many, but one of it could be transactional workload on database management system. They are mostly random in nature. So sequential IO, disk operates in most efficient mode, spending less time. If we have a sequential IO, then disk would spend less time in seeking and rotating, but rather more time in actually transferring the data. So more time in doing fruitful work, which is actual transfer of the data. Let's say that for sequential IO, the bandwidth that we get for the disk in its best performing nature is S megabytes per second. And for random IO, the bandwidth that we get is R megabytes per second. Now, definitely you could assume that if it's a hard disk, then S is way greater than R. If it's other modern disks such as SSDs, then the random access latency of SSDs have been reduced, or random access bandwidth have been increased compared to hard disks. So then, but still sequential, like S is greater than R, even for SSDs as well. And latency, we could measure latency in terms of time, so which we could just measure by the parameter t seconds. That if we issue one IO of size D, then how much time does it take to complete this IO of size D? And we could issue the same IO of same size D for different RAID algorithms. So that would not matter. We can directly compare the time that it takes for this D data. So thus, finally, to conclude RAID 0's discussion, for RAID 0, steady state throughput what is the steady state throughput for sequential read for RAID 0? Because we are utilizing all the disks that we have, we are using all the disks N. Let's say if we have N disks, then we are going to use all of them. And if the sequential throughput of each disk is S, so N into X. Now, what about sequential writes? I would give you a minute to think about sequential write, random read, random write, and also in terms of latency, how much, if we are measuring in terms of this parameter t seconds, t, then how much time a read would take if the time it takes to perform an IO of d amount of data, d amount of read on a single disk is t, then how much would it take for RAID 0 in terms of t, and how much time would it take to perform write? Again, if the time it takes to perform a write for d amount of data on a single disk is t, then how much it would take to perform the write of this d amount of data on the RAID 0 in terms of t. So think of all this. Take a minute. It's not easy. Probably you already have answers there. Okay, well, many of you might be thinking, Professor said it's not easy, but this seems easy. Yes, it's easy. If you're paying attention and if you understood RAID 0 and everything that we discussed until now, it's easy. So what are your answers? So sequential, right? It would be again n into s because we have n disk. For random read, it would be n into r because we have again n disk. And similarly for random write, it will be n into r. In terms of latency, because there is no redundancy, we are just, every logical IO is translated to a single physical IO. So in terms of the time that it takes to perform read, it's t. The time that it takes to perform write, it's t. The RAID 0 is the easiest to analyze. Now let's talk about RAID 1. As we already talked, RAID 1 is about mirroring. So after looking at RAID 0, where we didn't have redundancy at all, what is the straightforward idea that comes to your mind if you want to have redundancy? Well, rather than just saving a single copy of any data, let's store 2 copies of the data. So if one of that disk fails, then at least we could get that data from that another copy that we already saved, right? Very simple idea behind RAID 1. So while we think about reading, then do we have a choice in sense of where we read things from? Okay, yes, if we store data in a single piece of logical data into 2 physical disks, then we would have a choice where we want to read it from, right? Disk 1 or disk 2, if we are storing it on 2 disks. So in terms of reading, we'll have a choice to read from anyone. Now, many of you must already be thinking, okay, how does this choice to reading from one translate to the 3 metric of parameters, capacity, performance, and reliability that matters to us? Good, keep thinking. We would be getting there soon. In terms of writing, do we have a choice? If we are following this mirroring structure, not quite, because then we would have to write to both this disk. So no choice. And we would have to update both. But still, this update to both can be done in parallel. So let's say again, sticking with our example of 4 disk, D0, D1, D2, D3. When we have logical IOs of block 0, 1, 2, 3, something like that, then if we are implementing RAID 1, what we would do is block 0, we would store 2 physical copy of that. Let's say on disk 0 and disk 1. Then block 1, again, we would have to store 2 physical copy of that. Then block 2, again, 2 physical copy, block 3, and so on and so forth. Now, definitely, Some other possible alternatives to do almost the same thing physically in a different way could be block 0, you write it on this 0 and this 2. Block 1, then you write it on this 1 and this 3 in terms of how data is coming. So if a write for block 0 and block 1 comes together, we could write it together and then just a redundant copy of them together. Then if a write for block 2 and block 3 comes together, we could write them on the striped disk and then write redundant copy of them as well. So these are just different possible ways how we could mix and match, how we could do physically. But irrespective of these different physical ways, what we are doing is when we have a write, we would have to maintain 2 physical copy of that write. So write to 2 different disks. And when we have a read, we have an option. Now, which one of this we want to read it from? So then let's jump to our analysis. In terms of capacity, how we are doing with RAID 1. Okay, right? Not excellent, because if we have 4 disks, we are losing half of the capacity of that. We are effectively using just the capacity offered by 2 disks out of 4 disks, because half of it we are just storing the redundant data. So capacity is N into B divided by 2. In terms of reliability, how are we doing? Much better than RAID 0, because in terms of reliability, now we can tolerate 1 disk failure to up to N over 2 failures, depending upon, why do I have 1 to N up to 2 like a variance over there? Why not just exactly equal to 1 or exactly equal to N by 2? What would it depend on? Which disk fails? So in this example, we can tolerate the failure of disk 0 along with the failure of disk 2, or disk 0 along with the failure of disk 3, or disk 1 along with the failure of disk 2, or disk 1 along with the failure of disk 3. But we cannot tolerate failure of disk 0 and disk 1 both, or a failure of disk 2 and disk 3 both, because then we would lose that data. So depending on where we are storing redundant copies of data, we could tolerate failure of at least 1 disk, right? Definitely at least 1 disk, but up to disk N by 2. And now our favorite metric of analysis, performance. How do we do in terms of performance for RAID 0? If we talk about the throughput, how are we doing in terms of sequential read? Oops. Sequential write. Start thinking. It's your job to fill this table. And it's easy, it's not tough. So you can do that. How are we doing in these both cases? These all the cases for throughput and latency. Oops. Well, when we think of read and write, logically, the first thing that comes to my mind is read. We have a choice. We are reading only from one of the copy that we have stored, right? We don't have to read from both. So it would be same as what it would incur if I'm reading from a single disk. But write, now if I was writing to a single disk, then that's just the single write that I do. But now because if we are writing to RAID 1, then we would have to do the mirrored write as well. So it's an additional work of the double the amount of proportion, right? Every write needs to happen twice. So then with that logic, if it's sequential read, then the throughput which we would be able to perform to our best is do you have this table filled? Okay, time to check your answers. So for sequential read, it's n into s over 2. Hold on your horses. Yes, over 2. For sequential write, it is still n into s over 2. For random read, it is n into r, no, over 2. For random write, it is again still n into r divided by 2. While in terms of latency, because we end up, if it's a read, we end up reading the same amount of work as we would do on a single disk. But if it's a write, then we end up writing 2. But now both of this we could still write in parallel because there are 2 different disks for sure. So the time that we would take is still t. Anybody able to think why do we have sequential read and sequential write and into s over 2? Thinking with an example seems like a good approach. So what example can you take? Let's say in this type of distribution, we have a big sequential read. Sequential read ranging from 0, 1, 2, 3. Then depending upon how we are storing these blocks, what would happen? We would have a choice to read any one of these, any copy of 0 from any one of these 2 disks. Let's say we decided this one. Then we would have a choice to select copy of 1 from any one of these 2 disks. Let's say we took this one. Now when we have, next when we go to read 2, if we choose the disk that we want to read from for 2 is this, if that gets selected, then we are at the disadvantage, right? Because then we are not able to use the parallelism, but rather both this reads of 0 and 2 would happen from the same disk. And again, the same issue if we choose the copy to read the 3 from is this, then we would have the same problem. So in considering this factor into our picture, depending on where our reads are scheduled dynamically, we would end up having cost of n into s over 2, especially for sequential reads. Why we do not have that for random reads? Because for random reads, the chances, there is a high likely chance that we wouldn't have to do it like in the order. It's the read could just span over different blocks here and there. And because the read is spanning over different blocks here and there, a random read could happen to 3, then a random read could happen to a block ID 196, something like that. And because this is randomly issued, it's high likely chance that it's randomly distributed on this 4 disk. So we cannot say that surely we'll have this degradation of factor of 2 for random read, but there are high likely chance that we'll be able to avoid that. So it's n into r. While when we talk about writes, as we know that we have to do for every write, physically we have to do 2 copies, like every logical IO leads to 2 physical IOs. And that's why definitely for both sequential and random, we would have degradation of T of the factor of 2. So moving forward, now in any RAID where we are storing redundant copy of the data, such as what we are doing here in RAID 1, redundant mirrored copy of the same data twice, we would have problem of consistency. Let's say we are done, we got a logical write, we are done with updating this write to one of the disk, but while the RAID box was in the process of performing this write onto the second disk, there was a power failure. So it didn't went through successfully. What happens then?